Hi guys, today we'll be talking about Nitinol. So, what is Nitinol? Nitinol is nothing but a nickel titanium alloy, and the most important characteristic for us today is shape memory. So, what is shape? So, we'll talk a little bit about Nitinol and then we'll come to SMA. So, Nitinol is NITI is nothing but nickel and titanium, and NOL stands for Naval Ordnance Laboratory, where this metal or the substance was discovered by Bueller and colleagues in 1962. The composition consists mainly of 55% nickel and 45% titanium with slight variations, and trace elements such as copper, iron, and chromium may be added to adjust the transformation temperature. So, I'll tell you what that is. So, it has mainly two phases, the Martensite phase and the austenite phase. So, Nitinol, when it's manufactured, is manufactured in a certain shape which is called the original shape of the alloy. What happens is, and that shape is maintained at a particular temperature. So, what happens is in the Martensite phase, which is at a lower temperature from the manufacturing temperature, the Nitinol becomes softer and a twine structure which allows easy deformation, and due to this characteristic, it can be molded into any shape required according to our requirement. So, what happens is, once it reaches the austenite phase, which is at a higher temperature, it returns to the original shape at which it was manufactured, resulting in a stronger, more stiff structure, which is and also results in compression across the fracture side. This I'll explain better with the diagram. So, another important concept is called the transformation temperature range. It is the temperature range at which the Nitinol changes from its moldable form to its original form, resulting in compression at the fracture site. Normally, the TTR is 32 to 38 degrees Celsius to match the temperature of the human body. And it is a solid phase state change, which means that it does not change from a solid liquid into a solid again, it changes from one solid to another directly. And the reversible nature of shape memory alloy is another thing we should keep in mind. It can go between the Martensite and the austenite phase depending on the temperature over and over again, and it's not a permanent change at all. Okay. So what happens is, as you can see, this is the original shape, which is like a V, and it's opened up in the Martensite phase as it's moldable in the Martensite phase into a U-shaped structure, and this is two bone holes are drilled in the bone, and these arms of the staple are put inside the bones. These are the bones, and as you can see, once it's put inside the body and it reaches the body temperature, it gets back its original shape and creates compression across the fracture site, which is what we want. So, two important effects: shape memory effect and superelasticity. Shape memory is the ability of the deformed Nitinol to return to its original shape when heated to the austenite phase, which is what I just explained. And superelasticity, reversible strain recovery up to 8 to 10% under mechanical stress without permanent deformation, and this occurs at the austenite phase temperature. What this means, I'll explain now. As you can see, the curve for stainless steel, at 0.5% strain only, the steel undergoes permanent deformation, and it does not, and once it's deformed, it cannot return to its original shape. Whereas Nitinol can return to its original shape and undergoes reversible deformation till up to 8% strain. So up to 8% strain, it's totally reversible and it can return to its original shape, which is an important characteristic for us. For an example, when a Nitinol spinal rod can bend up to 8 to 10% reversibly with the body movement without any permanent deformation, and once the body movement is over, it springs back to its original shape without any permanent deformation. Most commonly used in staples, and these staples are mainly used for small joint surgery such as first MTP joint fusion, midfoot fusions, hindfoot fusions, and wrist and hand arthrodesis, and these provide dynamic compression across bone ends. An example of a device is PME speed, which is used nowadays. Second use is in intramedullary nails, where the nails are compressed, and when put into the medullary canal, the nails expand and there's more endosteal and bone contact, resulting in better stability. Bone plates and screws, as I said, Nitinol has is superelastic and reduces stress shielding across the fracture site, which is important for us because it helps with fracture healing. Also, shape memory screws. The screws are compressed, and once they are inserted into the plate, they expand and hold the osteoporotic bone more firmly. As I explained about the spinal rods are manufactured with the lumbar lordosis and thoracic kyphosis in mind, and once they are put in a deformed spine, they tend to return and try to correct the deformity back to its natural phase once the rod is heated in the osteocyte phase. It comes back to its original shape and tends to restore the lumbar lordosis and kyphosis, and hence helps in correction of the deformity. Advantages: excellent biocompatibility and non-corrosive due to the formation of titanium oxide film, and constant force delivery and compression, and MRI safe. And disadvantages is its expensive, difficult machining, and nickel sensitivity is a possible thing. So this is an example of a Nitinol staple used in first MTP joint fusion, and the most important thing for us is to provide compression across the fracture site, which is important for fusion. Okay, thank you.